I didn't.
All right.
I gotta be down.
Welcome back. Was it Monday? I think got me all confused. All right, we're gonna start. You guys got a little taste of freedom and you won't shut up. So here's the thing, all the same announcements apply. You can still apply to go to do biochem in Scotland next summer. That will be fun. Your midterm grades, I posted that this morning. It's just straight 90, 80, 70 scale, no pluses and minuses. So, you know, if you made a 80 or a 90, things look way better than it probably is. And if you made a, I don't know, 71, I don't know. There's a lot of variance. It's only like super accurate if your grade ended in a 5. And I've talked to a bunch of you, like there probably will be some amount of curve at the end, but we won't really know that until we see the final scores. All that is to say, you know, it's called a midterm grade. It's not the halfway point grade. It's really like one exam out of a bunch of points. Exam 2 is going to be in class on Wednesday, October 26th, chapters 12, 13, 19, and 20. So we were talking about whether or not I got a fall break. I didn't teach lab last week, which meant I didn't email my lab anything last week. I basically tried to act like for the whole week I wasn't teaching a lab course. And so we were supposed to have a spectroscopy. Most of you will be having a spectroscopy midterm in lab on Wednesday. My students will not. Do you feel lucky? All right, well, you're going to have it the next week. And yeah, before you point it out, I'm completely aware that this exam is also next week. So my midterm exam and my midterm spectroscopy exam in lab, it's in the instructions there. It will be short. It's not like an exam, hours long, 100 points. I mean, it'd be a lot of points, but you're going to have to assign the peaks for one of the products we've made so far this semester. So it'll be pretty straightforward. You can start preparing for that. I promised in writing that I would give my lab a full week's notice for that exam, so I can't really not do that. I can't move my Wednesday lab to another day. Too late to move this exam. So anyway, that won't be ideal, but you have 10 days. We're gonna, here in a minute, I am gonna start talking about chapter 20. We'll probably more or less finish. I will have shown by the end of today basically everything I wanted to show about chapter 20, and we can work problems and think about some synthesis on Wednesday, and Monday will sort of be another problem solving preparation for that. Okay, questions? All right, so like I said, chapter 20, carboxylic acid derivatives. I guess I should have written this stuff up earlier, so you can follow along with me, right? So we've got acid chlorides. Again, a carboxylic acid derivative is going to be a carbonyl that's bonded to something that's not a carbon or a hydrogen. So a carboxylic acid is a carbonyl bonded to an OH. So the carbonyl is bonded to an O. You replace that O with a chlorine. If the O is, and there was some confusion about this on the sort of practice exam we had on Wednesday. There was a box just to fill in. If you look at my old exams, there's a lot of those. So if a carbonyl is bonded to an oxygen, most of the time it's going to be an ester. But if that oxygen is bonded to a second carbonyl, it's actually called an anhydride, and it behaves quite differently. Then we have the thioester. R is not equal to hydrogen. We have the ester. R is not equal to hydrogen. We have amides. Sorry, 2 R's there. We have the nitrile. And down at the bottom, we have carboxylic acids that are in equilibrium with carboxylates. Right, so that's just an acid-base equilibrium. As I said on Wednesday, that is an acid-base equilibrium that's really important under physiological conditions in any kind of like biological tissue. The pH typically for living organisms on Earth, somewhere in the vicinity is 7. It's actually a little bit, well, for humans, for definitely, I don't actually know most animals. You'll read a lot that human pH is 7.4. All right, well, that's actually, I've heard that called physiological pH, 7.4. That ignores the fact that we are not, you know, I've talked about us being like a bag of water with a skeleton in it. Those are usually my bad days. Like, human beings are just bags of water. But we clearly aren't bags of water, right? Like, if you cut open a human, hypothetically, you find lots of different compartments and bits. And even on the cellular level, then, if you look at a cell, right, you've got this very hydrophobic membrane on the outside, and then you've got compartments and bits on the inside. Right, you go to Winston Hall to learn about those bits. So the pH of the various compartments varies considerably. So the pH of your mouth is a lot lower than 7, it's more acidic. The pH of your gut is like 1, right? So you can't drink 1 molar hydrochloric acid. Do not do that. But if you could somehow get 1 molar hydrochloric acid into your gut, it would just sit there and be like, yeah, this is what I am. Like, your gut is really acidic. And we'll see some reasons for that today. You really don't have anywhere in your body that the pH is way above 7.4, but in the bloodstream, which is kind of what we think about, like that's usually where the pH sits. All right, so at pH 7.4, right, the pKa of a carboxylic acid is 4-ish. So pH 7.4 is above 4. It's more basic than 4. So the carboxylic acid is usually going to be deprotonated if it's in your body. Not in the gut, but pretty much everywhere else, carboxylates will look like this. I'm going to talk about that some, probably on Wednesday, maybe again Monday, definitely when we do the amine check. All right, and so then I had this whole bit. We can come from any of these down to here by hydrolysis. All right, so hydrolysis is just breaking off this X group with water. And we can do this under basic or acidic conditions. Up top, nucleophiles will add to acid chlorides faster than they'll add to nitrites. I guess I should go all the way down to the bottom. All right, so nucleophiles will add to acid chlorides really easily, and hydrides really easily. Esters, they'll add, but it's slow. Nucleophiles really won't add to carboxylic acids. Right? The other thing that happens here is if we want to move down, we can do that. All right, if I want to take an acid chloride and turn it into an ester, if I want to go from an acid chloride to an ester, that's pretty easy to do. All right, so this is like a redox chart or something. Less stable is at the top, more stable is at the bottom. If I want to hydrolyze something, I just put it in water. I may have to catalyze it, I may have to heat it, but all I need is water. All right, if I want to go to an amide from a thioester, easy to do. On the flip side, going up the chart is more difficult. It's not impossible, but we have to do something to it. We have to shift the equilibrium. We have to use some sort of reagent. We have to kind of apply pressure to the reagent. I don't mean like literal atmosphere, you know, like gas pressure, but we have to drive the reaction up. And so I'm going to start there. Another one of these mechanisms. This reaction is very, very similar to acetal hydrolysis and formation. You guys hopefully studied some over the weekend and saw that. If you didn't, acetal, like you saw that the practice question on the exam on Wednesday, like you need to be able to draw the mechanism to make an acetal or to hydrolyze an acetal. Yes.
Did you say more or less?
Less. Just like a hill, right? So if I put a rock up here, we'll fall down to the carboxylic acid. If I want to go up, I'm going to have to do some work. All right, so an esterification, I don't like that. Again, this is going to be like we can have kind of anything over here. So first of all, just some terminology, right? If I say esterification, what I mean is I'm taking some substance and I'm turning it into an ester. I'm essentially going to remove water. So we would do this. All right, so I would add an alcohol to a carboxylic acid. I would get the ester. Again, an ester is going to be a carboxylic acid component, some group bonded to a carbonyl, and then an alcohol component. So we get esters by basically putting alcohols and carboxylic acids together and removing water. And in fact, that's true for a lot of these. To go from the bottom, to go from the carboxylic acid up, you basically need the nucleophile and then you pull water out of it. So water gets made over here. So this equilibrium, this is why I say it's like the acetal reaction. Right? If I want to make an acetal, I need to remove water. So I've got two equivalents of alcohol will react with a ketone or an aldehyde. They'll produce water. To drive that equilibrium, I remove the water somehow. I protonate it, I boil it off, I use a drying agent to suck it up, whatever. Same thing is going to be true here. And so really, if I want to make the ester, what I do is I run this reaction in the alcohol solvent. So like if I want to make a methyl ester, R prime here would be methyl. I'd run this reaction in methanol. To make an ethyl ester, I'd run this reaction in ethanol. And by having a whole bunch here, right, if I have an equilibrium and I add reagents on the left, it pushes the equilibrium to the right. And then I can also do something to pull the water out. So I'll write those possibilities down. Right, you can distill this off. You can distill the water out. You can use a drying agent. You guys have done this in lab, right? Magnesium sulfate, sodium sulfate. Or you can protonate it. That also works. Any of those three ways will drive this reaction. All right, so let's do the mechanism. So, do you think this reaction can be catalyzed by phase? What happens? Right, you might think, okay, let's just do this. Right? Couldn't the RO minus just add into the carbonate? And the answer, I see a lot of people shaking their heads. And I'm a professor and you're a student, so I have to tell you that, like, yeah, that could theoretically happen. But what?
Wasn't the OH about?
It's not that OH is a bad leaving group. It's that you get an acid-base reaction for it. So you have it. I could see it on your face. So this is completely plausible, right? RO minus is a good nucleophile. Carbonyl carbon is a good electrophile. The trouble is, this step is faster. That proton transfer is faster. So again, I've said this a bunch of times. I want to write it down. I'm going to erase this here in a minute. So And so if you ever have reagents and you look at them and you're like, these two reagents might react in an acid-base fashion. Like you've got a base that can take a proton from the acid. No matter what else you see going on, like that is going to happen first. Right? So even though this is a plausible thing, alkoxide adds to the carbonyl, like I'm going to draw something very like this here in a minute for a bunch of other things. Like if with any of these other derivatives, right? There's no acidic H over here. So the RO minus adding into the carbonyl is the only thing that can happen. Here though, if I've got a good enough nucleophile just to attack the carbonyl, it's going to be a good enough base to take the proton. Right? So this is why we really don't add nucleophiles very well to carboxylic acids. The carboxylate ion, it doesn't have an OH, an acidic OH. But now it's negatively charged, right? Nucleophiles want to react with partial positive things, not negatively charged things. So we're not going to go into it in this class. There are nucleophiles powerful enough to add to a carboxylate. Right, like a Grignard reagent, methyl lithium is the classic. If you take a carboxylic acid and methyl lithium, you can actually add the methyl to the carbonyl. It's a tricky, like doing it in labs, very difficult. It's sensitive to a lot of things. I think it's a bad reaction to teach. You might see it in the book. You might see it with if your lab professor does it, you might see that. So I want you guys just to kind of know, good nucleophiles are going to take the OH proton rather than do a nucleophilic attack. So we can't do an esterification under basic conditions. So this really can only be done, the Fischer esterification can only be done with an acid catalyst. Okay, so we need an acid here. All right. So we need any acid. Let's use sulfuric acid. That's normally would be my choice. You dissolve your carboxylic acid in a whole bunch of ethanol, add a drop of sulfuric acid, and heat it up. So what's the first step going to be? Which oxygen? Yeah, so again, we're always going to protonate here. And I'm going to show a couple of we've got two mechanistic paradigms here. So under basic conditions, we're going to get an addition elimination mechanism. So under basic conditions, right? Under basic conditions, the reaction is going to be driven by the nucleophile. The nucleophile is just going to attack the carbonyl carbon. We get a basic, right? So the nucleophile, basically what we're saying with basic conditions is this nucleophile is going to be a good base, strong base. Right, so it attacks, and then the intermediate we get is basic. Right, we're under basic conditions, we get this O minus. Then we do an elimination. We eliminate X minus, and X minus is going to be either a weak or a weaker base. That's not how we're doing it under acidic conditions. So under acidic conditions, it's similar, but the first step will be to protonate carbonyl. All right, so we have the nucleophile under acidic conditions. That nucleophile can't be a strong base. The nucleophile were a strong base, it would just be protonated by the acid that we have. And now we can have the nucleophile back. And this is just an addition step. So the same additional elimination sequence. And our tetrahedral intermediate is probably going to be acidic. It depends what the nucleophile is. But like if that's an ROH, the nucleophile here is going to have a proton on it. So then usually we're going to move some protons around. And then we'll eliminate XH. Right, so that stays acidic. Yeah. Right. Yeah. X has to be a decent enough leaving group, and that's why you can't really go up directly up. Right? Like if sulfur attacks an amine, you'd have to have an S minus kick out an N minus. Right? So then the leaving groups. Basically, once we get to the tetrahedral intermediate, right? This molecule exists, has no idea it used to be a different molecule. Right? So O minus is going to make the pi bond. One of these two groups, actually, in fact, the R group might leave, right? You've got three possible groups that can leave. The one that leaves is going to be the best leaving group. So if your nucleophile is a worse lead, or sorry, if your nucleophile is a better leaving group than the group that was already on there, it leaves. And a lot of times, like these are equilibrium. So the nucleophile adds in, it gets kicked out. It adds in, it gets kicked out. And what drives the reaction is some equilibrium shift. You pull out water, you do something else. These are the two basic paradigms that we're going to see. Nucleophiles are either going to add under basic conditions or acidic conditions. They're going to follow this general trend. It's going to be hard for folks at home doing this. If you're watching this, you can pause this, maybe take a screenshot and come back, and I'm going to talk about the Fischer esterification mechanism. Yeah.
Do we need to deprotonate that oxygen either?
You would need to deprotonate the oxygen.
Okay.
Okay, so let's run through this Fischer esterification mechanism. Carbonyl oxygen gets protonated. I went through this last time. Anytime we're protonating one of these carboxylic acid derivatives, it's always the carboxylic acid, or sorry, the carbonyl oxygen that gets protonated. All right, you're never going to protonate this. And the other thing, and I'm going to try to show this a little bit toward the end of class. All right, like some of this, and I know this comes off as just like I'm asking you to memorize it. I am trying to explain it like based on stability and likelihoods and acid-base chemistry. But this largely comes from, like there's experimental data behind this. Like I said, I'm going to show an example so you don't think I'm just completely making all this stuff up. The example's a little tough with this one. So yeah, memorize if you must. You can draw resonance structures. The carbonyl oxygen has more basic character than that oxygen, right? This oxygen can kick electrons up here, you get an O plus and an O minus. If you look at that resonance structure, an O minus is obviously going to be a lot more basic than an O plus. All right, so this gives us protonated carboxylic acid. Right, and then this is stabilized by resonance as well. This plus is really delocalized over these three atoms. And so now our nucleophile is not going to be RO minus. Like that's the one that everybody wants to use because I see by the product that I've got to add an RO in. So if I just take an RO minus in there, I get there really quick. Right? You're in the middle of working this terrible problem on an exam and you want it to be done. So just throw this thing in. I hope I marked all those. Should definitely grade that practice exam you took. You should have gotten an email from me that had the scanned version. I hope I marked that. If you use RO minus here, you're using a strong base under acidic conditions. That can't happen. So what happens is you use the protonated alcohol, a weak nucleophile, and it adds in. Right? And this is the lower line over there. Then we get a tetrahedral intermediate that is acidic. Right? Under acidic conditions, all of our intermediates are either going to be neutral or they're going to be acidic. Under basic conditions, everything's going to be neutral or basic. All right, now we have to move the proton around. And this actually requires a couple of sequences. So you can use the second equivalent of alcohol to take the acidic proton. You can't have this oxygen just grab this H, right? Because remember, the base has to come from directly opposite the oxygen that the H is bonded to, right? So this oxygen can't get the right geometry to take this. So now I get a neutral intermediate plus strong acid, and then either of these OHs can take that proton. Again, this curved arrow, the curved arrows always start with electrons, so they're going to start with a lone pair. In class, I should probably draw the lone pairs. Like I'll draw arrows from atoms. But you can only draw an arrow from an atom if it's got a lone pair. Right? So never draw them from an H, never draw them from a carbon. That other one, chapter 21, we're going to talk about negatively charged carbons. The atom has to have a lone pair. Never H, usually not carbon. All right, so what we've done, this last two steps, which I understand is, at some point they just start looking like lines to you guys. We've basically moved this acidic proton from the OR to one of the OHs. We've done that with a solvent molecule. And so this is actually called, and you can do this, I should have introduced this. I should have introduced this in the acetal mechanism. This is called a solvent-assisted proton transfer. You see, here's what happened. I drew the acetal mechanism up in class, and I looked out at you guys. This is, advanced human communication. I looked out at you guys, and you looked confused, and I thought, I don't want to add one more thing to it. So what's going on here, again, we've got an acidic proton on an intermediate. We need to move that proton to another atom in the molecule. That can't be done directly, right? There's no way for this atom to come around behind that H. You can see this by the number of atoms in the transition state, right? This H would be moving through a 1, 2, 3, 4 atom ring. You guys will recall from early in Chem 122 that 3 and 4 membered rings are not terribly favorable. So to move a proton like that, you can do that if I had, say, right? If I needed to move this proton, right, if I needed to move that proton to here, I can do that because this can bend around to do that. It'd go through a 6-membered ring. Can't do it through 4. I don't know if I clarified anything with that. So here's what this green SAPT does. It's almost like a get out of jail free card. You need to move a proton within the molecule. So don't draw this blue arrow, right? This is bad. Don't draw this blue arrow. It's not one step. You draw that blue arrow, I will draw a red stuff. But if you just write SAPT, you can skip this intermediate, right? So so again, SAPT, solvent assisted proton transfer. That just means basically the solvent grabs this proton and then immediately gives it back over here. The thing that grabs the proton can be a solvent molecule, it could be the conjugate, it could be HSO4 minus, it could be whatever the conjugate base is up here, it could be a water molecule, it could be another one of these intermediates, it could be the starting material. It's just some moderately basic molecule comes along, grabs the H, and just shuttles it over. It makes the geometry work. Okay, everybody hanging with me? All right, so we get to this intermediate, and now this one, this is all the proton transfers. I can now write this in, SAPT. So now we're at this point. Again, people often want to pull this proton off, right? Make an O minus and then OH2 plus. And then your O minus swings down, kicks out water, and you've got your product. But you can't have that O minus and a protonated oxygen sitting next to each other, right? You don't have any bases that will take that proton. So what happens is the OH makes the pi bond, and now the best leaving group available, like the R group's not a leaving group, OR would be an OR minus, a strong base. That's not a good leaving group, or it's not as good as water. Water leaves. And yeah, you got to keep that carbonyl protonated for the moment. We end up with a protonated ester. And now the last step, and again, this is some base. This could be water. This could be another equivalent of alcohol. It could be the starting carboxylic acid. It could be HSO4 minus. It could be A minus, whatever. Depending on the conditions, one of those things is going to take the proton. Right? It's probably under the conditions I've described where we're running the reaction in ethanol. So I've got a flask full of ethanol. Like there's a whole bunch of ethanol molecules in there. It's probably going to be one of them that takes the proton. And this gets us to the problem. Plus water. Piece of cake, right? Protonate, moves the protons around, add, eliminate. You really do want to think about, so there will be a lot of mechanisms possible on exam 2. I'm obviously not going to ask you to draw all of them. What you want to do is you want to break these mechanisms down into discrete steps, right? We've got a proton transfer step. You should know proton transfers really well at this point. You've got a nucleophilic addition step you're going to need to know. You've got an elimination step you're going to need to know. All the mechanisms are going to be combinations of those. We're going to protonate things, we're going to deprotonate things. We're going to have nucleophiles add, we're going to kick leaving groups out. Over and over and over. It's modular. So, if I asked you to draw the mechanism for acid hydrolysis of an ester, right? So acid hydrolysis, I would be going from the ester down to the carboxylic acid in water under acidic conditions. You guys ready to determine that mechanism? People nodding their heads. Cocky after fall break, like. So probably you're not, right? You haven't studied this. Like, I don't want to argue with you. You say you can do it, that's fine. I'm not going to actually give anybody a test for it. What I would say, if I agreed to leave this on the board, you should jump at the chance to take that test. Right? The hydrolysis mechanism to go from an ester to a carboxylic acid and aqueous acid is on the board. Right? You start down here with an ester and water and acid. You protonate the carbonyl oxygen. I guess I didn't draw water here. I probably wouldn't ding you for that, but I would ding myself, right? Water will add, we'll get a protonated tetrahedral intermediate that's got an OH2 plus. We're going to move the proton around. Now we have to move this acidic proton to the OR. We come back to here through a solvent-assisted proton transfer. All right. Now the OH is going to make a pi bond, kick out alcohol. And the last step is A minus or something takes that proton. Right? The mechanism of hydrolysis, acidic hydrolysis of an ester, the mechanism is exactly the same as, the intermediates are the exact reverse of the Fischer esterification. Again, proton transfers, nucleophilic additions, elimination of leaving groups. Logic. Questions? I have a question like what I'm supposed to talk about next. Oh yeah. All right. That's a lot. It's going to be on video. You can go look at it again. I'll give you guys at home one more chance of looking at this. Actually, I'm going to leave that there for a minute. How about I just leave that very important slide there? Come all the way down here. The seventh inning stretch. Yeah.
Is this supposed to just be like, like new free fill you had? Like,
For carboxylic acid derivative. Yeah, everybody, this board here, the third panel, this applies to everything. I'm not going to do in class every mechanism interconverting all these different groups. Right? If you read the chapter, it's extremely long. It's way longer than it needs to be. Right? If I want to go from an acid anhydride to a thioester, I can do that really straightforward. The RSH is going to be the nucleophile, the leaving group is going to be acetate, and it would be run under the basic. Right, so again, you've got basically three modular steps for all these mechanisms: proton transfer, nucleophilic addition, elimination. You just have to identify what's the nucleophile, what's the leaving group. So like I said, I'm going to come down here on the end and do a couple of quick reactions that I want to make sure you guys know you need to know. So the first is the reaction of thionyl chloride. Thionyl chloride is SOCl2. If you ever use this reagent, use it in a fume hood. Really pretty nasty. If you treat a molecule that's got an OH on it, the thionyl chloride, almost all alcohols or carboxylic acids, the OH will turn into a chloride. All right, so the way that works is, let's do it. So SOCl2, chloride's a good leaving group. Mechanism, this is basically an SN2 style mechanism. Again, the carbonyl oxygen is the basic atom and the nucleophilic atom of a carboxylic acid derivative. So then this gets us H plus Yeah, I hate this mechanism. So I have this nicely written out on a sheet of paper that is currently sitting on my desk in my office. Trouble coming downtown. Okay. Then you have chloride is going to attack. Chloride minus attacks that positive. That looks great, right? Now, what's the best leaving group? Chlorine is not the best leaving group. That's the right word to use. Chlorine is usually the best leaving group. You guys might remember tosolates and mesolates from Orgo 1, sulfonic esters. I would like you to remember that. In my mind, it's an ideal world. You remember that. Taxes are low, profits are high, we're all happy. Right? I understand you guys might not have even seen, depending on who you had for lecture. Like the thing you really need to know coming out of Orgo 1 is chloride, bromide, iodide are the good leaving groups. Really, any weak base is a good leaving group. So saying chloride's a good leaving group here is absolutely correct. What happens then is this. And chloride is kind of driving this. So the OH will kick out O minus. I guess I should probably just make that be. We get the protonated acid chloride, and then we get this weird looking thing there. And this decomposes, the O makes a pi bond to the S, we kick out chloride. Chloride ion will take that H. This gets us to our products. What do you guys think about that? Good. Really, I put that up to make you like long for the Fisher certification. I will not ask you this mechanism on the exam, but I want to use it to illustrate. I want to illustrate something. So anytime that we need to go from a carboxylic acid up, if you come over here and look, I said, right, remember me saying if we go from the carboxylic acid up, we got to do some work. We're going to put something in that will drive us that way. And so what you need is usually you need to turn the OH or the carbonyl O into a much better leaving group. And if you do that, then all of a sudden, like that leads you up. And we have hundreds of reagents that do this. SOCl2 is one of them. Like you guys can memorize this, but like I said, I won't ask you to draw this mechanism. Some of you probably had to in Orgo 1, depending on who you had. The other ones that you can use here, you can use PCl3, you can use PBr3. PBr3 would obviously turn you into an acid bromide. But all these reactions work by turning one of the two components, oxygen components in the carboxylic acid, into a good leaving. And at that stage, then, now you just do what you always do. Nucleophile attacks, the good leaving group leaves. Right? The weird part of this mechanism is getting to here. At this point, we got a protonated carboxylic acid derivative where this is a good leaving group. Chloride now is our nucleophile. We kick out the good leaving group. All's well. There is one other reaction I want you guys to know that follows this. And then I'll be done. Well, no, it's done. So the other reagent is this reagent called DCC. probably not. I'm not gonna go through the whole thing. It does exactly what the SOCl2 does. Right, so really what we're doing is we're using a fairly unstable reagent. It's what we're doing with SOCl2. Thionyl chloride, inherently unstable reagent. Like if I bottle it, I keep it away from air and water and nucleophiles, it will sit there kind of unhappy. As soon as it sees water, it liberates SO2, sulfur dioxide gas, which is toxic, smells really bad, and HCl. So if you ever get to use thionyl chloride and you kind of get a whiff of it, it'll wake you up. The SO2 is actually killing cells, and the HCl is tearing up tissues in your mucous membranes. DCC is a lot milder. It's dicyclo, the first two D's, or the first two. The DC is dicyclohexyl, right? There's 2 cyclohexyl rings on it. Those don't do any chemistry. The last C is carbodiimide. So you've got a carbonyl carbon, sorry, not carbonyl. You've got a carbon double bonded to 2 nitrogens. You think of a molecule that's the same oxidation state as. You guys know about, there's a very common molecule that has the same oxidation, carbon has the same oxidation state as the central CO2. Yeah. So CO2, we don't draw the structure of CO2 enough. We just say CO2. I'm going to draw the full, you guys should see the full Lewis structure. If nothing else, this molecule is going to take your beach home someday, so you may as well see the full Lewis structure, right? The carbon is linear, it's sp hybridized. It's got 2 really electronegative atoms bonded to it. This carbon is actually super electrophilic. And a lot of CO2 sequestration strategies rely on having like beds of polymer bound nucleophiles. You pass air over it, nucleophiles react with carbon, fix the CO2 on the surface, get it out of the air, and you put it somewhere and you do something with CO2. So this carbon is also, the DCC carbon is quite electrophilic. Right, so what happens is the carbonyl oxygen of the carboxylic acid reacts with that carbon. You get this activated ester, so you've got the O bonded to all this DCC molecule. And then what gets spit out, then if you put a nucleophile in there, the nucleophile will attack that activated ester, and you'll get whatever you have here. So the other thing you'll get is dicyclohexyl urea. DCU. Again, you're not going to have to reproduce that, but I wanted to add 2 things on that. You soak up water, right? This reagent's basically soaking up water. So DCC plus water gets you the dicyclohexyl urea. So dicyclohexyl urea. So what is urea? Huh? Very good. That's the next question. Where does urea come from? Urea is just a carbonyl with 2 NH2s on it. Also, that carbon is in the same oxidation state as carbon dioxide. And yeah, there's urea in your urine. That's also not going to be a test. Not a drug test. Pretty good. I never did mean to leave that. I am actually going to talk about some experimental data. So let me show you how you might use that. I don't want to erase anything. You might see that. You might see a reaction. Let's do this. draw the product of that reaction. Give that product, and you want to give the last thing we'll do with class today is talk about the mechanism for this hydrolysis rate. Give you another minute or two. So in that DCC reaction where I'm asking for the product, like it is in many ways just a straight up memorization. DCC is just going to couple nucleophiles and carboxylic acid. This is a massively important reaction. Okay, and again, coming over here on the DCC part, it's that carbodynamide in the middle that's important. So you will find diisopropyl carbodynamide used a lot. You'll find carbodynamide used where you've got, water soluble ionic constituents instead of cyclohexyls. These get used this reagent gets used in the pharmaceutical industry and in protein synthesis. So, you may have read about automated protein synthesizers that take amino acids and just stitch them together. There's a carbodynamide used in basically every step to make the anthol. So the reaction is, there's your carboxylic acid. Nothing else is going to change. All right. If you look at this, you've got a nucleophile, you've got a neutral nitrogen. That's a good base, a strong base, good nucleophile. That's going to be your nucleophile. The carboxylic acid is going to be your electrophile. The DCC is going to stitch it together. What's going to happen to the stereochemistry? I get some inversions. Racemic, just guessing. On the one hand, I haven't shown you the mechanism. It occurs to me as I'm lecturing and I'm about to tell you that you're just guessing. I didn't actually draw the damn mechanism, didn't I? So the mechanism, and you were happy about it a few minutes ago. The DCC reaction gives us this activated intermediate. CY is going to be cyclohexyl. And then the nucleophile does that. All right. The nucleophilic atom attacks the carbonyl atom, the carbonyl carbon atom. You get this intermediate. The intermediate, the O minus kicks out the activated ester bit. The point is in the mechanism, nothing ever happens to these two stereocenters. So those two stereocenters stay exactly the same. You get inversion if and only if you have an SN2 reaction on the stereocenter itself. I always love this question in Orgo 1 because it's like the easiest 5 points I ever take from anybody. Kidding. I don't like taking points. Like seriously, if I wanted to take all your points, I'd just take all your points. That's no fun. I like taking my colleagues' points. I like telling, John Lukesh and Angela King they're wrong. And they like telling me I'm wrong. So the question I always ask is, I do SN2, and I do some where like, I do a whole bunch and just look like the whole formula, right? Nucleophile attacks the carbon with the leaving group is chiral, nucleophile attacks it, inverts it. But if you have a stereocenter that's not on the stereo, on that where the leaving group is, nothing happens to it. And invariably, a lot of people, as they're learning this, like I can think it's instructive. The only stereocenter that inverts is the one that gets attacked. So when you guys think about mechanism, those arrows are telling you what's changing in the molecule. If an atom or a bond doesn't have an arrow to it or from it, leave it alone. It's not going to change at all. And this is also something I did on the practice exam that we did last week. Many of you drew some arrows that are perfectly good arrows. Like you have these curved arrows that make sense. But then you draw an intermediate that doesn't reflect what happened with those arrows. The intermediate also makes sense. Like you draw a perfectly good molecule. It's not pentavalent. Groups haven't moved completely over the molecule. You totally could have that intermediate in your mechanism. Just the arrows don't get you. So my advice as you're working on a mechanism problem, right? If you forget what you're doing, because I don't want you memorizing all of it. I want you to be able to think through it logically. If you can memorize it, power to you. But as you're working it, if you're like, the next intermediate looks like this, you can draw that intermediate, figure out what arrows you need to go from the intermediate before it to that structure. Likewise, if somehow you've got in your mind, I need these arrows, cool, go with it. But then draw what those arrows give you. Like each arrow is going to either break or make a bond. Do those things. So here, if we go through this mechanism, that nitrogen is involved, and it's going to lose an H. This carbonyl carbon is involved, and it's going to lose the OH. We're going to lose H2O in this reaction. And so just to make sure, I'm going to draw this exactly the same, because when I drew that up there, I was like, I'm going to have to turn it, like, if I draw this the same, then I've got to flip that molecule over, and now some things that were in front or behind, it's a pain. Draw this the exact same. Right. This nitrogen is not going to be bonded to that carbon. We're going to lose the OH. Carbonyl carbon, nothing happens to what it's bonded to. So there's a benzene. Meta is a methyl. Meta is a bromine. So that's your problems. Right. So again, ECC is just going to stitch together a nucleophile and the carboxylic acid. You're going to lose water. You're going to lose one H off of the nucleophile. One H is going to come from the nucleophile, and the OH from the carboxylic acid. And the only atoms involved are the carbonyl carbon, the nucleophilic atom. Questions about these? And that also, if you come back over here, right, I said you had to do some work. So if we have a carboxylic acid and we want to go up, we can use DCC. DCC and whatever the X component is over here. Or we can use SOCl2, right? We could start with carboxylic acid, go all the way up to the acid chloride, and then use some reagent to come down. Those two things generally accomplish the same thing. And in fact, I've talked about how we can interconvert, like we can always go down. Like I could make an amide from an ester. Almost always, if I really wanted to do that, I would turn the ester into a carboxylic acid and then come back up with DCC. Yep.
Does it matter if it's an acid?
DCC is always just run with DCC. And, I mean, that's kind of a basic solution because it's got the DCC just runs. Take a couple of minutes and try to come up with a mechanism for this one. I'll give you like 4 minutes to do it. Yeah. The DCU part of the molecule, the H gets shelled. It's a wild thing. Well, except the ester wasn't that. That was it. It was an oleic, like fat, it's olive oil. So olive oil is. I'm gonna probably blow this. Glycerol. Right. So the fats tend to be, so oleic acid, olive oil is 1, 2, 3, 4, 5, 6. So olive oil is this, it's oleic acid. And it's this double bond. So we'll come back to this. You guys made soap in lab a few weeks ago. We haven't taken those yet, have we? We're gonna get those. All right. So the fat that we hydrolyze olive oil is oleic triglyceride. So triglycerides are the esters of glycerol, and that's mostly what our fat is. You've heard of monounsaturated fats? Monounsaturated. Polyunsaturated fats would have a whole bunch of double bonds. Saturated fats, no double bonds. So you can take the unsaturated fats and hydrogenate them, and H2 over the double bond. You get saturated fats. I actually, yeah. So they didn't. Right. And so when you guys hydrolyze these, you put it in the hydroxide, as here, oleic acid comes off, it becomes oleic. And that's the soapy bit, right? You've got the hydrophobic tail, hydrophilic cap, the glycerin then either lost in the water, or it gives, if anybody's ever played with glycerin, it's super slippery. And it gives you a little bit of oil. So if you guys don't do this, but if you drop concentrated sodium hydroxide on your skin at some point, your skin becomes slippery. And the reason it becomes slippery is that the fats in your skin are hydrolyzing. Hydroxide is way more dangerous and destructive to biological tissues than acid. Everybody's always like, oh, acid, we gotta watch out. Phase will go right through. Okay, we got 10 minutes left. I'm gonna come back to this mechanism in the middle. This is the saponification mechanism. Are you guys debating mechanisms? Cool. What happens first? Nucleophilic attack. Good, you've been listening. So the first thing that happens is the OH minus attack. Right? I wrote that down. You guys You guys have been paying attention, so we get this tetrahedral intermediate, that's basic, the conditions are basic. I lost off. Don't do this either. Count your carbons, that's a pretty common mistake to make. Now what? Makes, right, we kick out OCH3. Why do we kick out OCH3 and not OH? No. No. It's about the same. The answer is they can both kick out. So this is a point where OH and OCH3 minus are roughly the same base strength, roughly the same quality of leaving group. It's 50-50. So the next thing that happens is we get carboxylic acid. I think I actually did this in class the other day. We get carboxylic acid and methoxide. And you're done, right? Hydrolysis makes carboxylic acid. We're not done. The reason we kick out methoxide here is methoxide cannot take this proton. And that gets us our product. So you can get methanol and carboxylate. We're under basic conditions, so carboxylic acid is going to be deprotonated. Right here, we've got a strong base, pretty decent acid, so you get an acid-base reaction. And that's why we kick out OCH3. OCH3, 50-50 in terms of which one gets kicked out. But if we kick out if we kick out OCH3, hang on, what am I doing? If we kick out OH, we just go back up to here, right? There's no acid-base reaction that can sort of finish the reaction. Here, if we kick out OCH3, we come over here. This last step is essentially irreversible. Right? I need a little back there. What was the question?
Do you have to draw like lithium plus charge floating around?
You don't have to, and I never do. I have a bad habit of never considering cations. I'm anti-positive things. If you want to, please. And probably, holistically speaking, it would be a good idea.
Do you have to draw it through like every step, just like floating?
Yeah. Well, I'm not gonna. If you just wanted to put it on at the end, that'd be fine.
Okay.
All right. Let me ask you this. Did anybody do this? Anybody draw that mechanism? Why not? Why? You can tell me why. I'm going to go out on a limb and say the reason you didn't do that is because of the third panel over there and me like yelling at you all about nucleophiles attacking carbonyl.
Is it because the carbonate carbon, like trying between the two all have more like opposite of?
Yeah, so that's our explanation. So the mechanism on top is correct. This mechanism does sometimes happen. It only happens with a methyl. Because what is the mechanism on the bottom? You had to put a name on the kind of mechanism. Not elimination. It's an SN2, right? Nucleophile, electrophilic carbon leaving. Sorry. So here's the thing. We know that now. And again, this class is still, even though it's Orgo 2, it's still really an introduction to organic chemistry. Nobody here would be, I'm not going to call any of you an organic chemist just yet. You might well be. You might go work in somebody's lab. You might, you have potential. I'm not trying to, criticize you. I'm just saying it's still introductory chemistry. So there's a lot of you just like throwing crap up on the board. Learn this. Tell it to me again later. 100 years ago, 100-ish, 120, 80, something like that. Long time. Nobody knew. Like, you could draw these two mechanisms and nobody could tell. Both of these were proposed. Like, how does the hydrolysis happen? We know there's all this empirical stuff. Again, we made soap, right? When did humans start making soap? After the scientific revolution? No, they made soap a long time ago, right? Soap's been around forever. Same with ethanol. People have been making ethanol forever. Right? So this chemistry was known, but nobody knew whether it was this mechanism or this mechanism. So here's what I want you guys to do, amongst all the other stuff you have to do. Come up with an experiment that would differentiate these two mechanisms. We'll do this in class. Like, it's 2 days. There are no points associated with it. If you're totally slammed, but as you're, like, look, when you're in Religion 103, sorry, like, and you're bored, I don't know, Abraham did something, like, think about this mechanism, right? Abraham didn't make enough soap, so why? What's the mechanism? All right. So come up with a mechanism, come up with an experiment that would let us distinguish the top mechanism from the bottom mechanism. And the last thing I want to say about this, all jokes aside, all the mechanisms I talk about in here, right? It's not hypothetical. Somebody at some point proposed a mechanism, and then a bunch of people went and tested it. Like, a mechanism properly is a hypothesis. Right? We don't, for a lot of these, we don't actually see the intermediates. It's a hypothesis, and if you can come up with, it's like any hypothesis, you test it. We do hundreds of reactions. And as soon as you just find a reaction that doesn't fit the hypothesis, that mechanism's wrong. Right? So, anyway, that's it for today. I'm going to be outside for a little while. And then I posted office hours this morning. Oh, one last thing. I have a lot of office hours this week. I'm trying to put together a review session for Monday night. My office hours this week, I will also be doing chemistry major advising. Those are like appointments that somebody has to get these things signed and filled out. And so I'm getting our office hours for 15 minutes to go with the student. All right, you're free to go. See you.